In this video, we're going to learn about the concept of an inner product. In our previous video, we learned about dot product, and that was specifically something we did in R2 and R3. And the idea of inner product is a way to generalize that concept to other, maybe more crazy vector spaces. Basically, mathematicians looked at dot product. They said, what properties are essential for the dot product to have in order for it to be useful to us? They narrowed it down to 4 conditions, and then they said, well, anything that has these 4 conditions will also be useful, and we're going to call that an inner product. And so here are the 4 conditions. The first is that it's symmetric, in that if you do dot product, it doesn't matter which order you write the vectors in. Or in this case, if you do an inner product, it doesn't matter which order you write them in. And this is maybe a little bit weird notation here. You could just as easily write U dot V to indicate dot product. But because we're doing things that are in, like, say, functions, rather than regular vector spaces or polynomials, we use this different notation to indicate that it might not be the normal dot product, it might be some weird new thing. Regardless, we want it to be symmetric. We also want it to be, maybe call this additive here, in that if you're adding vectors inside, or you can also call it distributive, think about this in terms of dot product. We want to be able to distribute in, and that's what property 2 is telling us. Property 3 says that if you have a constant, you can pull it out of the dot product, or the inner product here. And property 4 is maybe the only one that seems particularly off or different than the rest. It says that if you dot product or inner product something with itself, it can never be negative, and the only time the answer is 0 is if the vector you started with was 0. So it turns out that this last condition is actually very critical in solving problems with this. And if you don't have it, it is definitely not an inner product. There are kind of pseudo inner products that don't satisfy that. And mathematicians have looked into those and tried to see if they're any good at all. And they do have some uses. But for us, we really want to have all 4 properties. And if we do have all 4 properties, that is going to be called an inner product. And the first little fact here that I gave you is that the normal dot product that we have does satisfy all 4 of these properties. Therefore, it is an inner product. It's an example of it. However, there are many, many, many more examples of inner products that we haven't seen yet. The first example I'm giving you here is that if you want to take the dot product of 2 vectors in R2, x1, y1, and x2, y2, I can do my normal dot product, put an extra 5 here, and you can check it will still satisfy all 4 of those conditions. That 5 doesn't change the properties. But what that does is that 5 gives more weight to the y-axis. It basically tells us that moving along the y-axis is maybe 5 times as much as moving along the x-axis. So a random real-world application, let's suppose you're trying to move some heavy object from place to place. Well, it's going to be more work to move the object up than it would be to move it side to side. Right? If you move it side to side, you can put it on wheels and roll it really easily. Whereas if you need to move it up and down, you might need an elevator or some sort of pulley system, some other thing to get a really heavy object up. So putting that 5 there is just indicating that the y direction is somehow more important than the x direction for this particular inner product. Now we also have an example here of if I have continuous functions, and that's my vector space. Well, if you do, you can actually define an inner product by using the integral formula. And if you haven't had calculus yet, feel free to ignore this example. But it turns out that if you multiply the functions and do the integral of them, that's going to be another inner product that's going to be useful in a lot of applications of this. Okay. With all that said, what are we going to do with inner products? Well, we're going to do the same thing that we have done with the dot product in the previous section. We're going to use it to calculate the angle between vectors. So you may remember in the previous section, we had the formula that cosine theta was A dot B over the length of A times the length of B. We're going to do the same thing here, just using a different inner product than the normal dot product. Otherwise, it's the same thing. What's going to happen is we're actually going to get a different answer for the length of the vector, because it actually matters whether we use the normal dot product or this new one. So for example, this new inner product that's basing the y-axis to be somehow more important, well, that means if you go in the y direction, that's going to increase your distance more than if you went in the x direction. So let's actually work it out now. So we need to calculate three things. We need to calculate the dot product, and you can feel free to write it like that or our new notation like this. And these are our two vectors here, and we're going to use this formula where we multiply the y times the 5, so it would be the x times x plus 5 times y, and we'd have 2 minus 75 is negative 73. Then we need to calculate our length, but again, this is not your normal length. It's not going to be square root of x squared plus y squared, because what you have to do is you have to use a new inner product here. You inner product a with itself, and then you square root it. So this is going to be the square root of x times x plus 5 times y, and it's going to be the square root of 126. Notice the original length would have just been the square root of regular 26, not 126. Then we calculate the length of b here. That's the square root of b inner product with itself. Square root of x times x plus 5 times y. And let's see here, it's going to be square root of 49, it looks like, which is 7. So that means I have cosine theta is a dot b over the first magnitude times the second magnitude. And we're going to go ahead and use our calculator here to do cosine inverse of that. And when I plug it in my calculator here, I get theta is 158.3 degrees. So again, if you were to draw out your xy axis, this would not be the right angle. This would not be the right angle because this is not our normal dot product. But what this would be is this would be something like making your hash marks in the x-axis like this, 1, 2, 3, and then on the y-axis making your hash marks, erase that there, make your hash marks 5 times as long, 1, 2. And so it's saying that when you use this type of scaling, where the y-axis scales 5 times larger than the x-axis, if you drew the picture on that type of graph, then you get the angle of 158.3 degrees. So this is the idea here for how we can use inner products to find length and angles, even though it's not our normal dot product.